So now let's get into the Hubble tension.
Ah.
The Hubble tension.
Yes.
Now, when I think about the Hubble tension, sometimes, man, I'm going to be honest. I love me some nerds.
Yeah.
But I don't always vibe with the nerds.
Okay.
And why do I not vibe with the nerds? Because sometimes I feel like they're making too much out of a topic. And so the classic example to me is whether or not black holes have hair. Right? I'm just like, is it really that deep?
Right.
Yeah. So the Hubble tension, where does that fall?
Much bigger deal to me.
Much bigger deal.
Well, okay. So going back to this idea.
Define it. What is it?
Yeah. Well, so what is the Hubble tension? Okay. So we reach a point today where we say we kind of think we have a pretty good model of the universe, but, has big areas of ignorance. 95, 96% is in the form of dark matter and dark energy that we have kind of cartoon-like explanations for. But that's fine. Okay. And then we say, all right, let's really test this model. Let's see if it's really right? So what I've been calling the best end-to-end test of the model, right? You do an end-to-end test when you really want to know, does my thing, operate as I expect. The best end-to-end test of the universe is to look at the cosmic microwave background, which tells you the state of the universe shortly after the Big Bang, okay? And it allows you to predict how fast the universe should be expanding today. It's like if you had a kid who was 2 years old, you could predict what height they will grow to based on growth charts and your understanding of human physiology, okay? But the end-to-end test of that story is to actually measure today, how fast is the universe expanding? A number called the Hubble constant. That would be like measuring that kid's height when they are fully grown.
Right.
If you really understand things, the two will match within the error bars, within the uncertainties. And so over the last decade, we've seen this mismatch growing and growing in significance. First, it was 1 or 2 times the error bars away. Then it was 3. Then it was 4. Then it passed 5. Now, in physics, 5 is considered the kind of gold standard for like going from don't bother me with that to like, this doesn't make sense. And now we're probably up to 6 or 6.5. Okay. And the reason that it has grown is because the data is getting so much better. We've had the Hubble Space Telescope. Now we have the James Webb Space Telescope. Previously, we had crude parallaxes. Now we have the ESA, European Space Agency Gaia mission measuring parallaxes. The cosmic microwave background data has gotten better. First it was ground-based, then it was WMAP, then it was Planck, and now it's also these ground-based experiments with high resolution like ACT and SPT. So, and then we have many techniques for making these measurements. So when we measure the Hubble constant locally, we build what is called a distance ladder.
So speaking of that, I just want to define a term. You mentioned parallax, which is a geometrical way of determining distances, and it works best for nearby objects, but you can cross-calibrate more distant objects where they overlap. Right, something of that nature.
Yeah. And that process we call the distance ladder. I mean, ideally, you would look at some distant galaxy and you would measure its distance from us geometrically by looking at parallax. The parallax is when the Earth goes around the sun and your perspective on a nearby object changes with respect to something distant. You form a triangle in space and you can measure how far away it is. The problem is things are far away. They're really far away. So that shift in position becomes imperceptibly small. And so like you said, you can only measure it for stars in the Milky Way, but you calibrate the luminosity of a certain kind of star called a Cepheid variable, whose period, the rate at which it pulsates, correlates tightly to its luminosity. And so then you see one, you calibrate one that has a 20-day period with parallax, then you look in a supernova host galaxy and find more 20-day Cepheids, and you go, it's the same kind of object, just further away. Now I know how far away it is. Now I've calibrated the luminosity of the supernova, and this is called a distance ladder.
You build it up from nearby objects that you get a very precise distance to and move further and further.
So at the turn of the last millennium, astronomers used this technique to get the Hubble constant to about 10%, and that was great. But over the last 20 years, we have been improving that, now approaching about 1%. And ever since we got to about 5%, we started seeing this tension.
So different techniques give you different answers?
Well, really that the cosmic microwave background route, starting from the early universe and using the model, gives you a lower Hubble constant than when you measure locally around us with many different techniques. So that, more and more it starts to look to people like, the problem isn't in the cosmic microwave background measurements. They've been duplicated and replicated. The problem isn't with the local measurements. They've been duplicated and replicated. The problem might be with the story we tell ourselves that connects the two. This lambda CDM model, maybe there's something else going on that we haven't yet understood. Maybe dark matter and dark energy are more complicated. Maybe there's been more episodes of dark energy than inflation at the beginning and dark energy at the end. Maybe there's been a in-between dark energy. And so these are the things that people are thinking about, because otherwise we don't know how to explain what we're seeing.
So there's so the cosmic microwave background radiation comes from 13.5 billion years ago.
Correct.
This local measurement that you're making with the
comes from
supernovae,
now, essentially.
Now, essentially?
Close. I mean, redshift 0.05. No, not even. No.
Not even?
No, I would say maybe 200 million years
Oh,
back.
wow.
Yeah, so it's really
that's
now.
a big gap.
Yeah.
Oh, boy.
Yeah,
Okay,
yeah,
so
yeah.
what's the solution to filling in that gap?
Well, what you
the
would like,
observational solution?
Yeah, what you would like is you would like to be able to measure something in between where you had an absolute knowledge of distance. And so this is always the big rub in our field is I want to start out with something that's absolute, that it's like running a tape measure out and going this many inches, right? But instead we get lots of these standard candles or standard rods or things where we go, well, it's uniform at least. So if I see it here and I see it there, I could tell how much further away it is. And so this clash really comes down to the clash between parallax, which is the geometric sort of starting point for distances nearby, and at the other end is physicists' theoretical understanding of something called the sound horizon, which is it's the distance that a fluctuation in the early universe can travel from the moment of the Big Bang until the universe becomes transparent a few 100,000 years after the Big Bang. And so this is like a standard ring for them. They could calculate it from first principles. And so each of us are starting with these absolute references at opposite ends. It's like that famous meter stick in France that is kept in a refrigerator. It's like this is the meter, right? So we each have our this is the meter, and then we use tools to try to bring them closer together. But when we hold them up next to each other with these other tools, they're not agreeing.
Oh, geez.
So
that's tough. So.
No, it's great. Actually.
Well, it's great from your perspective.
Yeah, because this is how we learn things in science. It's the opportunity that we get. I mean, 1998, things didn't fit either. They didn't fit the conception at the time. So to me, this is what makes science so much fun.
So there's a discovery waiting in resolving this tension.
I think so.
Potentially.
I think so.
Yeah.